Ready? Okay, so let's consider the case that the n is really big, that we have to do it faster, or we at least want to do it faster than n power 2. So divide and conquer. Now, because now we have numbers, how we divide numbers? It's like not like a cards, you can put half there, or array you can easily split in the middle. So the dividing is a little bit more extraordinary. But if you see the numbers as a sequence of digits, we can actually divide the digits into two halves. And the first half is more significant part, and the second half is less significant part. So you can actually divide. If you divide the bits, if you have 8 bits of this number, okay, what is this number in 10 array system? Ones, twos, fours, eights. Okay, we have 4, we have 8, so here come 12. 16, 32, 64. Okay, 64 plus 32 is 96. 108. Yeah, so it's this number, but as you can see, I can actually divide it, I can calculate separately, and then I just sum it down. And in binary, now you can see that whatever is here, they are independent on each other. Okay, now this is what is done. So we have this number and we divide it in the middle to two halves, and then we represent these two halves. Okay, what is the first two here? They are hundreds. So this is 36 times 10 power 2 plus 24. So this is the second half. And same way we divide it. So in general, what we are dividing into most significant and less significant part. So now two numbers x and y, I divide to s and t in the middle. So numerical representation is that the more significant part s has to be multiplied by k. And this is now k array system. So in our case in bits, k equals to 2. In this digit system, 10 digit system, k equals to 10. So it's just a multiplier. So here, and what is this power? So I multiply not 10 but 10 power something. In this case 10 power 2. So why 2? Because I have 2 here. So this is 2 digits. So if in total my number of digits is 4, n divided by 2 is 2. It's the size of the half. So this is the size of the half. So I multiply. In this case, 10 power 2, I have 3600, that's represent the first part, plus 24. So if I modify this example here, this 96, if I consider this as a separate number, so what is this one? This is 1s, 2s, 4s, this is actually 6. 6 and 12. But now I have to multiply it 2 power 2. 2 array systems, sorry, not 2, 4. 2 power 4. How much is 2 power 4? 16. So this is maximum here is 15 if all of them are 1. So the lower one here is 16. So whatever number I have, now I have 6. That has to be multiplied by 16. 6 times 16 is 96. So I don't need to calculate this sum it up, so I can just calculate independent numbers just like that. So now, with this representation, let's see, can we do, how we can now do it better. So idea is to divide that. We don't multiply long numbers, but we multiply smaller numbers. So, okay, so now we see, I have these numbers, I need to multiply the first one, sk power n divided by 2 plus t, multiplied uk n power 2 plus v. So how do we multiply? A plus b times c plus d.
b squared.
take all pairs. So I have two terms here, I have to multiply this by here, and this by this, and this. 4 pairs. So all of them I have to take. So what I will have here? First term. Okay, let me see. SKSU. Okay, the last pair is clear. TV comes here. Then I have a V times that one. So SV.
In the middle.
Yeah, it's this one times K power something, so it's here. Okay, then this one with the first one, T times U. Okay, I found it. And multiply this K power something, it's here. And the first pair, SQ, it's here. And now K times N by 2 times K N times 2 will become K power N. Okay, now I managed to do it. So now the trick is that what I have done here, I have more multiplications than before. If you look carefully, I have here, I have SU, I have to multiply these together, then I have to multiply SV, TU, and TV. In addition, I have K power N and K power N divided by 2, and these I have to multiply also. But these are the base numbers. K is our base number. It's 2 power something in binary. In our case, it's 10 power something. How much does it take to multiply 36 by 100? How to multiply 36 by 100? Do you need algorithm for it? Yeah, add zeros. So basically, in binary, bit shift left or something like that, or right, I don't know, bit shift left, I think. So whatever is your base number, that many steps you move it to the left. Okay, it's now, okay, base number is just move once, but then this power says how many steps you have to move it. So in this case, K power N, you have to shift N times. So that takes, well, it takes order N time, right? So it takes 10 steps. But if the multiplication takes N power 2, and I have to add some linear time processing there in the middle, who cares? It's so much faster that I can afford a couple of bit shifts. So basically this multiplying by base number is linear time operation, can be done fast. Also this one. This is actually N divided by 2, because N divided by 2 steps needed there. So I have, oh yeah, and I have the summations. How fast or slow is summation? Summing two numbers. Order 1, yes. So if I have two numbers and summing them up is really taking 2 digits, summing up, and 1 memory, and then sum it up. So linear time. So this sums is also n steps. Could be n plus 1 if there's extra memory going somewhere and so on. So all remaining challenging operations are these longer numbers, S and U, SV, TU, TV. Okay, now how much time does it take calculate TV? So how do I do it? Little equals coming there. Okay, divide and conquer. What I have done now, I have divided the number to halves in the middle. I have now reformulated the multiplication here with these half numbers, and I have come new formulation of the bottom line here, but I have some now other multiplications. So originally I have only one multiplication. Now I have 4 multiplications. What's the point? Okay, maybe it helps to look at the numerical example here. So now let's do it for this one. 3, 2, 2, 4 times 2, 3, 4, 5. If I multiply this using this new formula, what I will have? SU. So what is S? S is this one and U is this one. So I have 36 times 23 plus SV. Okay, multiplied. Okay, this has to be multiplied by 1000, I think. No?
100.
This is K power N. N is 4.
Oh, okay.
Actually 10,000. Then I have SV, so S is this one and V is here 45, so I have 36 times 45 plus TU is 24 times 23, and this is multiplied now 10 power 2, 100. And last multiplication TV is 24 times 45. This is my new formulation of that original multiplication. What is the difference? Understand, now I have more work to do than before. Before I had just one multiplication. Applying this to the school book algorithm n power 2, it's what? 4 power 2. 16 operations. I have here one multiplication, another one, another one, another one. What's the difference? Come on.
It's less digit than.
Yes, it's less digits. Which is easier to do? This one or that one? This one, of course. Here you have 4 digits, so it's 4 power 2. You need 16 steps to calculate it. Here I have only 2 digits. How many you need? 4. 3 times 4, 6 times 5, 6 times 4, this, and adding some zeros. So this, if you make the school book algorithm, it will have only 4 steps in the process. So this is much faster. Okay, I have 4 now here, but I have 4 of the multiplications to do. So let's see how this sums up. Okay, so yeah, so one thing is missing. So what? So divide and conquer. Don't look at this yet. Try to hide, not possible. So divide and conquer. I divide it to 2 halves. I have new formulation. I have new multiplications to do, but they are half of the size. What do I do with this? How do I solve them? I delegate to Radu. I have a long number, 1000 digits.
Yeah.
You will have 500 of them. Well, actually, yeah, you will have 1000 digits, another number 1000. I select one of these. I have the 4 of these pairs I need to calculate. First half here, first half here. I have these 500 digits to Radu. Please solve. Then I come to you. I have another pair I need to solve. To you, 500 digits. Solve it. You will have another one because I have 4 here. 1, 2, 3, 4. You will have the T and U, 500 digits. You will have the last one, TV, 500. What do you do with it? Come to the teacher and say, hey teacher, too difficult, I give up. I had 1000 and 1000 to do, and I split it.
I will split and give it to someone else.
Yes.
I will split it and give it to someone else.
You split it again. Recursively apply the same algorithm. Radu now has 500 and 500. Okay, he split it. 250, 250, 250, 250. He will have now 4 pairs there. And the guys behind him, and he needs 4 guys now. You are not enough, so he will take you and 2. You will have 250 numbers. You have 250, 50. And same. So you delegate further. Recursive call. So this is just divide and conquer. It's just a little bit sneaky way that you don't know, oh yeah, the data is divided. And now you can see the number of sub-problems is not 2 or 1, it's 4 subproblems. 1, 2, 3, 4. So instead of having one problem of size n, this will delegate to 4 subproblems of n divided by 2. I managed to divide it to half of sizes, but because of the multiplication, has to be done in this crossing. It's I have more subproblems. Okay, and as you can guess, this is not going to be good enough. It's a nice idea, but the end result will still be order n power 2. So let's see. Okay, so what I claim, because now I do this recursion, how do you solve it? It doesn't matter. You just call the same algorithm, so you delegate to 4 people there. And they have 125, 125. They will delegate, they will have 60, 60. Delegate 4, 30, 30. So you can see it's logarithmic number of steps, it goes to the 0 level, and you will be solved. So you need the recursive call. And because of the recursive call, to solve this one, we'll take recursive formula. So whatever my algorithm is Tn is, I use the same algorithm recursively, but half of the size. So this will take Tn divided by 2. And I have 4 of them, so you can see. All of them I need to solve. Plus I have this multiplications of these numbers n, summation n, this multiplication n divided by 2, summation n. Summing up all together, I managed to get 4 times Tn divided by 2 plus 4 times 4.5 times n. And guess what? Master theorem, geometric case. And the master theorem, I think it was
B greater than C.
Yeah, we have B recursive calls of size dividing factor C plus D times N plus E. So what we are really interested in is this C and B and their relation, and we will find out B is greater than C, and therefore time complexity is N times C-based logarithm of B. And that's what you have here. B is 2, and C is, oh sorry, vice versa, C is 2, and B is 4. 2-based logarithm of 4 equals to 2, order n power 2. You could solve it substitution method as well, but the key idea here is that able to do the analysis, you need to be able to construct this part. Half work done here. Coming to here is just, actually this is the easy part. Once you know master theorem, you're able to apply, then it's here. And then finally, drawing conclusion. Did we gain anything? Question?
Yeah, this algorithm's complexity is order n square, and the previous school level algorithm, which was also n
Yes.
order n square. So what's the difference? I mean, the difference is internal, or
So question is that the original algorithm has n squared and the new algorithm has n squared, so where's the difference? Okay, did anybody find the difference? Where is it?
I mean, in the study of complexity.
It's a valid question. Let the others answer. Schoolbook algorithm order n power 2, this algorithm also order n power 2. Which is faster? Or where is the difference? Okay, would you use this new algorithm? Okay, which is bigger? Order n power 2 or n squared?
Yes, they are the same.
No difference, they are the same. Nice idea, no cigar. Didn't work out. So I didn't get any improvement, I get exactly the same result. So I divide and conquer, but I failed to get improvement. So that's why these guys, Karachupa, Hoffman, they didn't give up. They continued to tune this formula, and tada, they find a new version. So sometimes the solution is not just simple as that, just divide and conquer. Sometimes you need to really find tricks, and here is a trick. And this is not obvious. I wouldn't have invented myself this kind of algorithm, but this is what we have already done, 4 multiplications. And then they figure out, but it's almost the same terms, S, T, U, V, they are repeating all the time, just in different order. And then they think, hey, how about this? But it's almost like this one, right? If you have S plus T multiplied U plus V, what will come out from here? Okay, let me see. SU plus SV plus TU plus TV. Okay, let's see. Oh, SU I have here. Okay, I have it. SV, I don't have it. TV, TU. So SU I have here, SV I do not have. TU I don't have, but TV I have here. 2 of the terms I have. Okay. So okay, so let's put it there anyway. So now I will put this one here. So it means that I must have these terms. But my resulting, how this go?
Inside there is a no SU. So minus SU, there is existing SV.
Yeah.
In the bigger. That's why the minus is always SU.
Okay, yeah, no, I'm mistaken here. This is, so yeah, so I compare this one, yes, I mistake. So I want to see that, hey, this one here, it's almost like that one, but not exactly. So I compare S and U is not there, S and V, it's there, it's here. So SV is there, TU is there, but TV is not. So now if I put this term, it's almost like this, but not exactly. But if I subtract, so this one equals to here, if I now subtract here minus SU minus TV, so it means that I can take away this one and this one, SU and this one. Now I have exactly what I had here. So if I replace this one by this equation, minus SU minus TV, then it equals to this one. So little trick, and what do I gain? Now if we look carefully, now we have 1, 2, 3, 4, 5 multiplication, even worse. But now there is a trick happening, because if we look carefully, we have SU once, SU twice. Hey, if I calculate it once, why should I calculate it again? I just store the result and apply when needed. So both of them is calculated only once. TV happening twice, again, only once needed to calculate. Now you see what's happening. So only thing what I added here, so I actually get rid of something, or I actually get redundant information here that's free of charge. And this one I need to add. Okay, one summation is linear time, another summation linear time. I add more summations, but only one multiplication. And if I have S plus T, if this has n digits, this has n digits, the result has at most n plus 1 digits. So with my level of accuracy, it's just order n. So, okay. So, calculating this now takes recursively Tn divided by 2, Tn divided by 2, Tn divided by 2, plus several more summations. Now I have only 3 real multiplications. So I have changed the formula now, or the result is now 3 subproblems, all half of size. I get one rid of. My constant work in the linear time work, this has increased. I have more the summations and more this linear time process. But because this is anyway going to be over when n grows really big, this start to go the insignificant at the end. So it really doesn't matter. So only this, but okay, the result from here, again from Master theorem, we now have v equals to 3. c equals to 2, it's still b is greater than c. Still same result, same equation, n power something, but now the logarithm is 2 base logarithm of 3, which is smaller than 2. It's greater than 1, somewhere in between, and the exact number is 1.58. It's not n log n. It's not as fast. With a certain number of n, it can be close, but when n grows, this will grow faster. But it's still significantly faster than n power 2. Okay, any questions? Copyrighted material, I didn't buy it. Let us keep it fast. Okay, we have still some time to go, so let's see. I was thinking to go the heap structure as the rest of the time, but we have less than 20 minutes to go. So I might take instead some extra material and leave the heap for next week.
It's one of the exercise questions,
Yeah.
but only a little bit of it. So.
Okay, anyway, stop the recording here, so to divide it.